Well, hello everyone. Good afternoon. Welcome to the latest IRIS webinar and the first one for the academic calendar for the fall 2016. This is your host, Danielle Sumi, speaking from the Incorporated Research Institutions for Seismology headquarters, which is in Washington, D.C. IRIS is a consortium of universities and an NSF-funded science facility that operates programs that enable Earth scientists to perform advanced research in geophysics, and in particular seismology. In today's research-focused webinar, which was solicited to highlight important science results, but especially with Rob and FuncLab on educational topics that hopefully will lower the energy barriers in your own scientific research. Webinars are recorded and archived on the IRIS YouTube channel, and you can always contact me if you have any questions about the webinar. Just to lay some ground rules, only the presenter, Rob Porritt, and I will speak. If you have a comment or question as the webinar unfolds, then please clearly and concisely type it into the box on the webinar control panel, and I will try to help you out. At the end, if you have a question, I will read your name and repeat your question to the speaker. If similar questions have been asked, I may simply combine them or skip one. If the webinar crashes, which unfortunately has happened in the past, I will simply reboot it, and so just use the link that you received by email when you registered. Also, at the end of this webinar, I will send out a short 5-minute survey via email because your opinions and insight help us to inform future webinars. One of the questions will ask if you are watching this remotely in groups. So if it's more than just you, please let me know. I wanted to remind also of this group that next week there's quite a few meetings. One is the Geological Society of America meeting that's taking place in Denver. I will be hosting an early career coffee that Monday morning from 9:30 to 10:30 at GSA in collaboration with Aisha Morris of UNAVCO. So please either stop by, if you're at GSA, stop by and see me at the early career coffee or at the IRIS booth. So today's webinar is part of IRIS's continued efforts to provide resources and tools that enable research and professional development. And this subject in particular was born out of the US Ray short course that's for graduate students and postdocs. Our presenter is Dr. Rob Porritt, who is a postdoc at the University of Arizona. Before beginning his postdoc at Arizona, Rob had a previous postdoc at the University of Southern California, where he used multiple seismic imaging methods, like receiver functions and ambient noise tomography, to image the Hudson Bay and the Banda Arc collision in southeastern Indonesia. Rob completed his PhD in seismology at the University of California, Berkeley in 2013, where he worked on seismic wave speed structure with regional imaging methods. And Rob has become a mainstay during our US Ray short courses. And this year he was one of the lead organizers and instructors, where he has discussed FuncLab and SplitLab, as well as 2 flexible array deployments that he helped install, maintain, and eventually decommission in Cascadia. So without further ado, here's Rob to talk about FuncLab. Thanks, Rob.
Thank you, Danielle, and thank you everybody who's attending or watching later. I'm going to be talking to you today about FuncLab, and particularly going over all its functionality, a lot of it that I've added, but as the title of this webinar states, I'm just one person, and this is really a community code that a lot of other people have contributed to. And I've also, kind of my main contribution here has been integrating other tools into this package. I found FuncLab to be a great way to kind of organize receiver function data and do a lot of things relatively quick. And as Danielle said, I've been working on this from my time at USC, at Arizona, and while a visiting researcher at Kobe University in Japan. So what is FuncLab? Well, it's a graphical user interface for managing receiver functions. It works in Matlab, so you have to have up-to-date Matlab license. It was originally written by Ken Meager, Matt Fouch, who have since were no longer in academia. So I've kind of adopted it and expanded a lot of the functionality. The main part has been to incorporate these other packages like processrf Matlab, which is codes for Matlab on GitHub from Ian Bailey, mmap, which is a free version of the mapping toolkit. There's also a fun little thing, CPT map, that allows you to read GMT color palettes into Matlab, Iris Fetch, which is fantastic way to get waveform data, event data, station metadata directly from Iris in Matlab, and MatTauP, which is an easy way to look at predicted travel times, ray paths, a whole bunch of different things. But right now, one of the reasons why I still don't have a paper written on it and have it as a full official release is that we don't have documentation. I just haven't had the time to really, time and focus to sit down and dedicate, a couple of weeks to really getting this into final shape. So everything I'm going to show you is still in a beta version, a little bit preliminary, but hopefully I'll show you that it does work for some very simple, straightforward analyses. So hopefully many of you are already familiar with receiver functions, as they're one of the most popular regional seismic imaging tools. But if you're not, I kind of want to go over some basis of it and some example analyses that have been done with receiver functions. So here you can see the basic idea of a receiver function, that we have some free surface with a 3-component seismograph at the surface. We have some layer at a certain depth, h, and the material properties in each one of those layers is considered a constant. The bigger the difference between the material properties in the two layers, the bigger the contrast we're going to see on the receiver function, the bigger the amplitude. And so what happens is when we have some teleseismic plane wave, such as a teleseismic P wave, at the material contrast, it converts some of that P wave energy into S wave energy, and then it travels up. But it's not just the direct P to S conversion. There's also a series of other conversions. And it just doesn't happen at one particular interface. It really happens continuously all the way down, since really the Earth is not perfect flat layer cakes like we wish it was. So how we calculate receiver functions is relatively straightforward. It's really a deconvolution of some incident waveform from another waveform that contains the converted waves. Generally, when we talk about P to S receiver functions, that numerator, which is not really right, that's kind of a frequency domain representation that really what we're doing is deconvolving the P waveform from the radio component S waveform. Or sometimes we rotate into P and SV coordinates so that we have SV over P. More commonly, we would just do radial over vertical as an approximation to the SV and P. And so what you get is something that looks kind of like this in a very idealized, simple case where you have at 0 lag time in the receiver functions, you have your direct arrival at big P, little p in the upper left diagram. And then you see this big P to little s conversion comes in a little bit later. Then maybe then there's a series of multiples, the PP, PHS, which is, well, you can see the ray paths in the upper left that map to these receiver functions. So there's been a number of papers that use receiver functions quite a bit. This is a relatively recent one in JGR by Stanchu et al. This is looking at the IDOR array in Idaho, and they have a very dense line that they focus on, as well as some neighboring stations in kind of a 2D arrangement. Here's an example of what some of the receiver functions look like. They've plotted these from west to east, and you can see the topography on the top is kind of a reference that shows that we have higher topography in the east than we do in the west, and there's a change along the western Idaho shear zone. And when we look at the receiver functions, we can see the direct arrival pretty well aligns at about 0. And then we can see this, they've circled a strange positive at about 3.5 seconds, and they've lined up with yellow dashed lines their MOHO picks at about 4.5 to 5 seconds. So this is actually a station stack of receiver functions, but it looks pretty close to a standard receiver gather, or well, it's a simple gather. So another tool they can use is called HK stacking. This is a method that was pioneered by Zhu and Kanamori in 2000. And basically, it's a stacking and search space to try and look at crustal thickness versus cumulative, or not cumulative, but the average VP-VS ratio in the crust. So that H is the thickness of the layer, and then the VP-VS is the relative P velocity to the S velocity. And so you can see the search space, we find a peak, and we find that peak, and we call that our best estimate from HK stacking. Down C, it shows you the variation of receiver functions at one station with back azimuth. And again, you can see a nice alignment of phases about 5 seconds. Looks like they have it labeled -5 here. So then you can also do, instead of looking at these in wiggle domain, you can do a CCP stack, so common conversion points. And in this case, they show very similar to that earlier profile where we were looking at the wiggles. We have a nice moho aligned at about 35, almost 40 kilometers. And then as we get into the Western Idaho shear zone, we have a break in the moho and a shallow positive pulse. But that was looking at the crustal scale. We can also look deeper with receiver functions. This is a paper I published recently in GRL that is looking at transition zone. So the question that we were looking at with this is, there's this deep earthquake. If you can see the moment tensor at 692 kilometers depth, we wanted to know how deep was the transition zone here. There's a slab that makes the transition zone deeper. We did a 3D migration to try and get our best estimate of what the actual base of the transition zone is. We found it to be about 390, and the JMA, Japan Meteorological Agency, found the depth of this earthquake at 682 kilometers. So yes, thankfully we did not change our idea of how deep earthquakes can happen, but we do have a very deep base of the transition zone here. And that is corroborated by other studies as well that have used other methods to get at similar base of the transition zone methods. So FuncLab, we've decided you want to try and get some converted wave imaging. And FuncLab is a way to kind of organize it. When you start up FuncLab from Matlab, you'll see a screen like this that tells you you can start a project either from existing data or compute receiver functions from some 3-component data, or you can also use web services to pull data directly. So you'll notice in the upper left there's a file menu. That file menu is where you can create or load your projects. You can also edit preferences and exit FuncLab. Sorry. There's also this compute tab, which has an option to compute new P receiver functions from raw 3-component data. So if we use that compute new RFs, it'll open a dialog box like what you see here. So you can set your deconvolution method. One of the standard, so this allows 3 different standard deconvolution methods. A water level deconvolution, which is basically in the frequency domain, and the water level is basically, it sets a minimum amplitude in the divisor to avoid dividing by 0. Then there's the iterative time domain method, which uses multiple iterative convolutions to try and get at a series of bumps, positive pulses, with a certain Gaussian width. And there's also a damp deconvolution, which is similar to the water level, from my experience. But generally, they all work pretty similarly. The iterative takes a little bit longer, but it's become kind of the standard. The water level, there's also been really good results with water level recently, so that's something to play around with. One of the ideas that I built as I worked on this methodology is it allows you to test different styles. So you could do a primary deconvolution with the water level, secondary iterative, have the same set of parameters, and just see how different they are. So it's something that allows you to kind of test a little more fully. If you click on the set parameters, another box will open up, and you can set a whole bunch of different receiver function parameters. You choose your raw waveform directory, so this is directories where you have your data stored. and then SAC file name. So it only reads SAC files, so you have to have them in that format. But the specific how you name the files, there's a lot of different conventions. And so I've programmed a few different file name conventions in that SAC file names pop-up menu. And then new project dir. So you're going to want to use the box to choose a new directory to put the project. So a little bit more carefully, what this requires is the data directory with subdirectories formatted as event, 4-digit year, 3-digit Julian day, 2-digit hour, 2-digit minute, 2-digit minute, 2-digit second of the event origin time. And just because that is important, have the anvil effect. One thing I've found, a lot of different people will use different directory structures. If you do, say, an ambient noise type study, you're going to want some type of continuous structure. But a lot of us do event-based data, and so I really kind of press for this to be a standard that a lot of people try to adapt, even if you're not just doing FuncLab receiver functions. But kind of have this standard as an easy way to pass things in your own work and to other researchers. For the compute, we're looking at east, north, and vertical. Compute will do the rotation for you. And we also need event metadata in the SAC headers. As I said, you can select your deconvolution method and your various filtering parameters, your Gaussian pulse filter, etc. The way this originally was built, and I think is still a very useful tool, is a project from existing receiver functions. And again, this requires the same event subdirectory format. Which again, I'm just going to harp on that I highly suggest that you use this format for any event-based processing. And then within those event directories, it's going to look for 5 SAC files per station, one that ends in .eqr, one .eqt, one that ends in .r, one that ends in .t, and one that ends in .z. And the ID I have in curly braces here because that's going to be the same for one station. So something like, say you're looking at station ANMO, it would be ANMO.EQR, ANMO.EQT, and ANMO.R, etc. And that would be in the directory that's event _year Julian day, hour, minute, second. There's a couple other things that it looks for in the SAC header. So I always just use SAC, and then CH for change header, and enter these variables for the Gaussian pulse array parameter. If you don't have that, you can calculate that with tau p. The edit status, so that's going to be 1 if you want it to be active, or 0 if you don't want it to be active in user 8. And the fit, which is computed with the iterative decon in user 9. I'm going to talk a little bit more about the edit status in a little bit. So this is what the project looks like once it's loaded into FuncLab. You'll notice that menu is still up at the top, and then this pull-down menu that says Station Tables. When we click that, it can change to Station Tables or Event Tables by default. After doing more processing, you can do HK tables for HK stacking analysis, or CCP tables for the common conversion point stacking. Right now it has the stations, they're listed, they have network name, dash station name, and then another dash. And you'll notice NW-HQIL-00. That 00 is the location code. And one thing I've chosen to do when we use Iris Fetch is that if you have a station that has a location code, that is now added to the station name so that you can have one station with multiple location codes without them being overwriting each other. So that's something that you can figure out how you want to deal with later. In the next box, we have records listed by events. You can see those are the event origin times. They have those same 5 bits of information as I've been harping on about the event time and the event directory structure. And then in the right, you can see a lot of metadata. Most of that is filled from the SAC header. So a lot of these are pretty useful kind of ways to just look at very quickly information about that station or about that record. Okay. So always the best option when you're doing a live test is to actually do something live. So I'm going to go ahead and load FuncLab from my own Matlab. I'm using academic use Matlab 2016A. It also works with 2016B, and it should be backwards compatible with many different versions of Matlab. Haven't tested them all. I only have a couple computers, so if you find an install issue, let me know. I can try to help you, but your best work is being able to try and figure out yourself. But the main code itself is just called FuncLab. So if I enter FuncLab from my Matlab terminal, it opens up that welcome screen that we saw before. If I go to File, you can see a few options here. These work like you might expect. We've all seen computer programs before, I hope. So there's an About tab that tells you the old email and homepage and that I'm working on it. We also have this option to do a new project from existing receiver functions. We can call iris fetch to create a project and load an existing project. You notice add data is grayed out. So once we have a project loaded, we can add new data to it. FuncLab preferences, we'll look at these in a little bit later once we have a project loaded. A log file, which is just a file that keeps track of all the processing being done, and exit. So I'm going to start by, let me go with, let's do a new project via iris fetch. I'm not actually going to go through this because it's very slow, because it's actually going to be pulling the data from iris. But I want to show you how the setup works. So I clicked on that, and the text is a little bit cut off. This is Matlab 2016A has something with their text positioning. But it says, please type the full path name for your new project directory. So I have to do something like, I'm in a directory / users Porritt FuncLab test. I can call this something like Wisconsin. Let's say it, Wisconsin, because say I want to do a project in Wisconsin. Click on this choose station map, choose station box from map, and it loads up this figure. Now I can use the Matlab tools here. I'm going to use the zoom, and I'm going to zoom to Wisconsin. Got near Minnesota as well, but we're going to go to Wisconsin. I'm going to check new rectangle, draw a box around Wisconsin and the western half of the Upper Peninsula and some other bits. Confirm. And now you'll see in these four boxes here, we have a max latitude, a min latitude, min longitude, max longitude. Find stations. This will actually call iris fetch. And now I have a table of stations available. By default, it shows me the network, station, latitude, longitude, and by default they're all active. I have a few buttons. I can select none, select them all, deselect a couple, invert. We can sort it however we want, or we can select by polygon, which is a fun little tool. So this is using G input, and what I'm going to do is just click points around just Wisconsin, so I can cut off Minnesota. And as a Michigander, I'm not very happy about using just Wisconsin. So let's see. There we go. I've clicked all around Wisconsin. I hit enter, and now you can see this polygon has selected just stations within Wisconsin. Close that window, and now you see my table has a bunch of stations that are deselected. Hit OK, and now this shows me a map of stations. So this just shows you all these Wisconsin stations. Close that. It works similarly for events. Let's just start 2009 to 2013. I think that's pretty close to when TA was there. We can set our time windows if we want. Set our magnitude window. Let's go to 6.5 and greater because I don't want to see a lot of events. Then I hit Find Events. and you see it's returned about 94 events. And again, this has similar selection tools. I didn't do a select by polygon tool, but it allows you to see things like the origin time of the earthquake, latitude, longitude, depth, magnitude. I think there may be something up with the Flynn Indall. This should actually be the actual location name, but as I said, we're still in beta mode. I hit OK, and it makes a map. You can see all my stations are here. My earthquakes are well distributed. And then we have this trace info box. This allows you to set the start time before or after in seconds. So you can either do it relative to the origin, the PKP, the S, or the SKS, as well as the end time. It allows you to choose a sample rate. It will do an interpolation and filtering to try and get that desired sample rate. If you want to do a response with full zero responses, that's also here. I have a tool for encrypted data if you want to do that. So this is great if you have data that's behind this, on embargo. And then various receiver function parameters here. For instance, how do we taper, if you want to do any tapering, 5 and 10% hand and handing tapers, filter high and low passes, filter order. These are time before and after the phased cut. So we're going to get a longer time window and then cut out a smaller one for the receiver functions. Set your numerator, set your denominator. This is experimental to change the source method between a single station, which is what we usually do, versus an array-based. You can set your Gaussian, which is a pulse, and change your method. In this case, I've only coded iterative and water level. And you can change your incident phase. When you click fetch traces, it's going to take a long time. It's actually going to go out and get the data. So I already have the data I need on disk, so I'm not going to do that here. But also, because whenever I think of FuncLab, I think of Funk. And so if you click on George Clinton, you get George Clinton.
So you're beautiful.
But that's a commercial in front of the YouTube. So let's go ahead and instead do new projects from existing RFs. So I need to create a new project. So I'm going to call it Michigan 2. I'm going to browse. So in this browse, I need to choose where I have the waveforms. So you'll notice that I have AZ data. I'm going to look at that a little bit later, maybe, and Michigan. So this is a project I've already worked that's based in Michigan. So you can see we have a whole bunch of folders here, but the new project's going to have many less. The key is this raw traces here. So raw traces contains the data pulled down via iris fetch, and you can see it has a bunch of event directories. I'm going to open that, because that's where my data is. Then I'm going to go to this, my main Matlab window to show you that structure. So you can see we have Michigan here, and then here's our raw traces. Under raw traces, we have the event, year, Julian day, hour, minute, second. Under that, I have the raw SAC files. These are in a format similar to MC to SAC version 2 output, but I've put dots and the decimal points between the hours, the minute, and the second. It's a little bit easier to parse. So these are the raw E and Z data. Let me expand this a little bit bigger. So now you can see here is network.station, EQR over vertical, iterative deconvolution, 200 bumps using a station deconvolution, a Gaussian of 2.5, .eqr. So this is the radial receiver function SAC file. Same thing, but ends in EQT. This is the transverse component. This is the .p, so this is the p component. R for radial, SV for the vertically polarized shear velocity, or not velocity, sorry, vertically polarized shear wave. T for the transverse component, and Z for the vertical component. So I have this for each station under each event. So I'm going to import these into a new project. So if I click Start, it's loading those data sets and creating a new project for me. If I go back to my main window, you can see Michigan 2 now exists. can ignore that red, that's a new Matlab error. But in the new project, all we have is our raw data, which contains that raw traces. It's an exact copy of the other data directory. We have log file, which just keeps track of all the things done, and project.mat. Now, project.mat is our main project file, and it contains a set of variables, record metadata strings and doubles. So these just give us all the information we could want about the data, all the metadata. We have preferences for FuncLab itself and trace edit. The table menu is something, and set management cell will look at that, and data statistics. So this is really the main project itself, is project.mat. So let me get rid of Keynote. So let's go ahead and set FuncLab preferences. So we have various things like the time axis increment, rate parameter increment. These all make a little more sense as we go through things more, but first I want to set the station map north longitude or north latitude to be 49. South latitude 40 I think is okay. West longitude, I'm going to go -92 to -80. Event map center latitude and longitude doesn't really matter that much. Few of the things we could notice here, you can set your phase arrivals for various plotting algorithms. 1D velocity models, there's 5 different 1D velocity models. We'll keep AK135. Map locations, we'll just go all. You could also set it to active versus inactive. We have various projections for our maps, and these projections are done through mmap. There may be something that checks if you have the mapping toolkit, but the mapping toolkit has changed its syntax in the last couple of years, so it might not work as well as mmap. So it's something to bear in mind if you have the mapping toolbox, which I don't. So I can go ahead and save my preferences. And now let's go to the, you'll notice all these other menus have many different options that are now lit up and available. So compute new RFs, this is something we looked at briefly. You can recompute the ray parameters. This is just something I had an error in earlier, and we can compute PRFs to depth. But I think what we're mostly going to be doing is this editing. So editing is simply saying if the trace is good, which is a little bit qualitative, we'll keep it. If it's bad, we'll get rid of it. And so there's various ways to do it. We have a bunch of different, basically 3 different algorithms for automated trace editing. They can either be working on just the selected station or on all stations. We can turn off dead traces, so I found that happens more often than I'm comfortable with. Or we could also import trace edits from a previous round. We also have trace edit preferences. If we open that up, see we can select which component we want to trace edit on. We can either do the radial or transverse receiver functions, or the raw vertical radial transverse components. Again, we have our velocity model prediction. We can set our y-axis increment. I found this to be pretty useful to set it to something like 2. Records in view 36 is fine. Begin time, I like -5. End time 20. This is because we're going to be looking at relatively crustal structure. We can also filter it if we want to. I found filter to be most useful if you're looking at the raw data, not the receiver function data. Let's go ahead and save that, and then go to the manual trace edit. This is where you'll spend most of your time. And so you can see here are our receiver functions. They're sorted by event origin time. You can see positive pulse kind of here. So this is probably our MOHO. So we've got crustal thickness a little bit thicker than the standard 35. We can deselect all, which is something that is very helpful when you have a lot of bad data. Or you can select all. You'll notice the color changed. The color is red by default when they have not been edited, and yellow by default when they have been edited. You can also sort them by various things, any of the event metadata in the record. So let's say you can sort by ray parameter, and it looked like it changed that back to not edited yet. We can sort by back azimuth. You'll see they changed the order a bit. Once we're done, we save edits. And then we can go and view into our View tab. So there's a lot of things under the View tab. For instance, seismograms. This shows you the 5 different components: the vertical, radial, transverse components, the radial receiver function. See, there's our MOHO, and the transverse component. This is going out 0 to 90 seconds, so it's a little bit too long. So let's go ahead and go to our preferences, set that time axis increment, go 5, begin time 0, end time, let's go 20. Also, I'm going to set the ray parameter to be a little bit finer, and the back azimuth to be finer. So we don't have a lot of data, so that might not look great. But if we view seismograms again, now we're looking only at the first 20 seconds. I'm going to do a record section. This shows you for all the events at this station. Maybe we can get an alignment of our MOHO kind of there. I find the other components don't always look that good. Stacked records. So this will show you this red line here is the stack of all the receiver functions. This is all radio receiver functions stacked. This is all transverse. One thing that's also useful is we can switch between station and events. So if I want to look at those same things, but now for the record section for one specific event, where you can see the vertical traces align nicely, the radial align nicely, our receiver functions align pretty nicely. So that's a pretty useful tool to switch between event and station tables. We can also look at record sections with MoveOut. So here you can see our radial receiver functions. Looks similar to one of the figures I showed you from the Stanchu paper. But we could also use what they call an image plot. So we've now colored positive pulses red, negative pulses blue. In the center, we have a radial receiver gather. So it's just the stack of all the radial receiver functions. And you can see there's kind of 2 positive pulses here. You can see that they kind of align from this guy here and this guy here. So that's with MoveOut. So that's against ray parameter, but you can also look at back azimuth images. So this is event back azimuth, and you can see it's still pretty consistent. Another way to look at that, this shallower peak is kind of decreased when we look at versus back azimuth. Dataset statistics is not terribly interesting. Gives you stations and events. See our station map. So this shows you where all of our stations are. All the black dots are all the stations in the project. This gold dot is our currently active station. So that means it's PNPO. We have a global event map, which sometimes takes ridiculously long to plot. So I'll probably just cancel that, actually. Or try to cancel it. Yeah. Control C to cancel things like that that are just taking too long. But it's just a global map with coastlines and whatnot. This shows you the data coverage. So we're looking at back azimuth of all the event station pairs along the azimuthal axis, and then the ray parameter along the radial axis. Let's see. Next thing, we can do PRF to depth. This actually doesn't take too long. So we can compute our P receiver functions from the time domain to the depth domain. I'm just going to do a 1D. You can also do a couple iterations with a 3D model. Okay. Only took 2 seconds to do that. But that opens up this new ray diagram option here. And so now we've seen all the receiver functions. So we have longitude on the x-axis, latitude on the y-axis. We can kind of play around with it. It's kind of tough sometimes to look at this, so what I like to do is actually just go to the Matlab itself and use the view command. So that sets our view to be, let's see, we have south on the left to north on the right. Versus depth in the y-axis. You can see the alignment of the MOHO pulse at about just over 40 kilometers, and then we can still kind of drag it around to look at it. So that's a fun little tool. The other thing that I've added recently is this subsetting tool. So let's say I want to do just Michigan stations. I'll use this polygon. And again, it's similar to the other tool. Let's make sure we get the UP. So I did my undergrad up at Michigan Tech, way up in the Keweenaw. And I'm just clicking around the state of Michigan, getting all the stations in there. Let's get the Isle Royal too, because that's a lovely area. All right, so now only stations in Michigan have been selected. You can see now this table has just the Michigan stations with the check next to it. I'll keep all events on. We can also set the fit parameter or array parameter, back azimuth distance. Set name, I'm going to call this Michigan only. And we can set colors. There's various preset colors. This helps you keep track of which set you're working on. If you have multiple sets, you can go with maize. We also have University of Michigan blue if you like that. We have various Michigan Tech colors and whatnot. Iris purple. Actually, let's go with iris purple since this is an iris webinar. So we create it, and you can see our background is now this iris purple. If I want to change back to the base set, I use the choose subset, confirm it, and now it's gone back to the USC cardinal actually for the color. Or USC's red, I forget exactly what it is. But yeah, we can go back to Michigan only, and now we have less stations. If we view our station map, okay, it's probably difficult to see, but the Michigan stations are now purple, and the Wisconsin stations are black. The active station up in the Keweenaw is gold. So that's an easy way to, if you have too much data and you want to look at a smaller region, subsets are an easy way to do that. And the other common tool we use is are in the add-ons. So we have one such as HK stacking. We can just run that HK stack. And it looks similar to the Stanchu paper. So we get various outputs from the HK stacking. Notably, we have this P to S. We're looking at a back azimuth plot. We're looking at an array parameter plot. And we're looking at a stacked record. So you can see that it picked the MOHO at this diamond with its uncertainties by the circle and the square. Not where I would put it. But we can see in this HK stacking space, it's got about a 30-kilometer thick crust, a very high VP-VS ratio. So something might be wrong with that. So we can play with these different parameters. I've got this manually set time window, which I'm just clicking on either side of that big pulse. And now it changes the search space. So we're going to see what happens when, okay, it looks like it didn't like that. It still finds the right P to S conversion. Looks like the diamond is a little bit closer on this 34-kilometer crust. But you can see the search space. We got a VP-VS of 1.97. It's not unreasonable. It's still kind of at the extreme limit, but this is kind of one way to try to get better HK stacking results. You can also run it through all stations. I'm not going to do that because that takes a while. We also have common conversion point stacking. This is one of the original add-ons, and you work through it one point at a time, but it does take a while, so I don't really have a lot of time to go through that. But basically, you would do 1D ray tracing, then 3D corrections if you want to do that, time to depth migration, assign the CCP stacks, and actually do the CCP stacking. I've written a different one. So the difference between CCP stacking and CCP stacking V2 is that the common conversion point stacking is a bin-centric approach versus common conversion point stacking 2 is what I'd call a ray-centric approach. So basically, as you're tracing each point along each ray, in the original version, you have to say, does this point in this ray go into this ith bin, and then go through all the different bins. Whereas in this version, version 2, it just says this point along the ray, which bin does it go into? And it's a subtle difference, but it basically means that you cannot have overlapping bins in V2, whereas in V1 you do have overlapping bins. But it's also very quick. So in this case, all we do is we set our geometry. We don't want a max depth of 800. We want, say, 200 depth increment, say 2. These are kind of big longitude and latitude increments, but it's fairly fast. And then we can run ray tracing. Again, 2 to 200. We're going to keep AK135. We're going to do just a 1D confirm. The ray tracing is already done. Run the CCP stacking. And so the CCPs is stacked. And now we're going to output a underscore volume.mat file. So this has just a 3D model of receiver function amplitude from each point, and a ASCII version of that. And so then we can do, well, first I want to go into this ray parameter back-azimuth stacking. It's a very quick, simple tool. It basically just stacks things into ray parameter back-azimuth bins. And this station hit chart shows you what that looks like. So here's our station. And it looks like most of our back-azimuths are this way, to the south. There's one over here to the northwest. And we have pretty much consistent all slownesses directly south. And when you do this, this is great if you want to use, say, Bob Herman's joint inversion code, because it stacks out a lot of the variability that may come from poor traces. One thing I want to show you, and since we're running low on time, this will probably be the last one, show you this visualizer tool. So this is a way to look at various data sets. So we start with just a globe, and then you can select model. There's a lot of different things. You can do like a CCP or CCP v2, 1D models. So here's AK135 plotted. Let's see. I've also have multiple 3D tomography models, such as DNA 13, which is part of my thesis. So you can load up DNA 13, you can make 1D depth profiles. So this is just shear velocity versus depth, or shear velocity perturbation versus depth. With a depth map, so let's say at 200 kilometers. And this actually is opposite what we're used to looking at. So I'm going to go ahead and swip the color map to val.cpt and redraw. So here you can see, say, the one through the slab, the base of the Laurentia craton, a whole bunch of structure stuff. It's relatively easy to use. You can make cross sections, fence diagrams. But let's go to our CCPv2, which is in the CCPv2 directory. Click on the volume.map. Now we want to set our geometry. We'll just keep component radial receiver function using ray theory. Save the geometry. And now we can make all these tools, such as a cross section. We'll just go up here from the Q1R down to Detroit. Various parameters we could set. We get an image that looks kind of like this. So maybe here's our MOHO coming in at about 40 kilometers, which is pretty reasonable for Michigan, being a basin. We could also say, let me go ahead and real quick change to a different project that's already done. So go to the original Michigan, which has everything done. We go to our add-ons, our visualizer, and we can do our HK thickness map. So this is just a plot of all of our crustal thickness estimates from HK stacking. I think a lot of refinement can be done to make this better, but it's a good start. Note that this also already has the CCP computed. So we can do CCP stacks.map. It's a file for that. Again, we can set our geometry. Looks like it's computing. So again, it zooms into Michigan. Cross-section. Now this model looks quite a bit different, so I'm trying to figure out why these differences are. But yeah, this one looks like it wants a 20-kilometer thick crust and another strong positive conversion at about 120 kilometers. So something might be a little bit odd about this, which is why I like the CCP v2. It looks to me a lot closer to the data. Let me load this up. Oh, I had my geometry set to increments of 0, so that's not going to work. The other thing that I wanted to show you guys was this compute new RFs. As I showed this a little bit in the presentation, but you can change water level, iterative, or damped. You can set parameters. So these are very similar to the web services version. But notice we can also change for water level how we set the water level. Max noise is kind of an interesting new technique that's being used. Raw waveform directory. So I'm just going to have some data for 4 events in Arizona, or the stations in Arizona. And let's go ahead and look at, oh, I can't go to that. But then I'm going to have to choose an output directory. So I'm going to call this Arizona. For the project, open. And when I run this, it's calculating new receiver functions. A couple little beeps, but I think it's still okay. We still have a project. We have raw data. We have events. We have our .eqr, eqt, rtz. Okay. So here's our stations in Arizona. So we got a station map. Station map's in the wrong place, but we can still look at some seismograms. Don't look particularly good, but that happens sometimes. So with that, I think we're getting at the end. I think hopefully we have a couple questions. If not, thanks for your attention.
Thanks, Rob, so much. That was really great. I think you present it in such a way that I feel like anyone could really come away doing receiver functions, and that's really amazing. And so I know in your intro you gave a little bit of background. While questions are coming in, feel free to put a question in the chat box. But I actually had one about kind of what motivates you. What motivated you? I know you gave a bit of an intro about people who had designed FuncLab and who are out of academia. But what motivated you personally to start working on something like this?
So it was actually kind of a challenge. It was at the short course in USRA short course in I think 2014, maybe 2013. Actually, Andy Frassetto from Iris was like, let's have a session on FuncLab for a way to show students how to use FuncLab. And he thought that I knew how to use FuncLab. I didn't, but I learned it. And it took me not too long to learn the old version. And I got frustrated with a lot of the things that we couldn't do. For instance, computing receiver functions. You would think something called FuncLab would be able to compute receiver functions, but it couldn't. So I said, well, that's not right. I saw some of the great things coming out of Iris, like Iris Fetch, and thought, okay, how could I incorporate this into this toolbox? And I worked on that. Getting ready for the short course, and turned out all right. A number of other things. I was waiting for data while I was in Japan. I was getting data from the NIED, and I had to actually go there, which was fantastic, to take the Shinkansen train and whatnot. But yeah, I was waiting for the data, so I just had this time to play around and started building these things that needed to be done.
That's great. Also, where can people find more information about what you talked about today? Or obviously they'll have the webinar for posterity, but where can people find more information about the software?
Yeah, so if my screen is shared right now, this is my WordPress site, and on my software I have links to this version of FuncLab. I also have an updated version of SplitLab that hopefully has the colors or has the plotting issues fixed and also incorporates iris fetch. We've also got a little bit more about the station analysis tools, another tool I've put together. Um, and then there's comments that you can ask on it. I try to respond um, when I can, but no guarantee that I'll actually respond to comments on the webpage. What I'd really like is once I actually have this in a stable enough version and I have the paper accepted, put it up on GitHub so that anybody can easily pull from it, change it, add it, update it. This shouldn't just be one hero code. It should be something everybody can use.
That's great. And so what do you feel like your timeline is for the manual and everything?
I have no idea, honestly.
Yeah.
Yeah.
So, all right. Well, great. I really thank you, Rob. I know that this webinar stemmed out of the short course and how we really didn't have a lot of time to go over this, and people were, kind of upset about that we didn't have as much time as we could have to go through FuncLab. So this webinar idea stemmed out of that, and now it'll be on YouTube, for everyone to see. So thank you so much, Rob, for your presentation. Thank you, everyone who was able to attend the webinar. And yeah, stay tuned. We're trying to do these Iris webinars once a month. So stay tuned for more information about what's coming up next. All right. Well, thanks, everybody. Take care. Have a good rest of your day. Bye, Rob.
Thanks, Danielle.